Assalamualaikum, everyone. The total mass of the protons and the neutrons when they are separated is always greater than the total mass of these nucleons when they are intact in the nucleus. This mass deficit is accounted for by what we call the binding energy. Join me till the end of this video to learn more about nuclear binding energy. Just hang on, watch and learn. The question is, for lead with atomic number 82 and mass number 206, or with an atomic mass equal to 205.974440 atomic mass unit, obtain letter A, the mass defect in atomic mass unit, letter B, the binding energy in million electron volts, and letter C, the binding energy per nucleon, also in million electron volts. The combined masses of the protons and the neutrons when they are separated from each other is always greater than their combined mass when they are intact in the nucleus. And this mass defect or mass deficit can be accounted for by what we call the binding energy. All right, it is the energy that holds and keep the nucleons intact in the nucleus, and it is determined mathematically using Einstein's equation, the mass energy equivalence, E equals mc squared. In this problem, we are given the atomic mass of lead 206, which is a stable isotope of the element lead with an atomic number of 82. And for us to be able to answer the three questions, we need the atomic mass, all right, of lead 206. That is equal to 205.974440 atomic mass unit, which is given in the question. Likewise, we need the mass of the neutron particle, given here as 1.008665 atomic mass unit. And also, we need the atomic mass of the neutral hydrogen atom, right? Which is 1.007825 atomic mass unit. So to compute the mass deficit labeled or denoted by delta M, right? We use this formula, right? The mass deficit delta M is just equal to the atomic number capital Z times the atomic mass of a hydrogen atom, denoted by capital M sub each, plus the number of neutrons, capital N, right, multiplied to the mass of a neutron, denoted by small letter m sub n, and then minus the atomic mass of the neutral atom containing the nucleus, which in this case is the atomic mass of lead-206, right? So each of the quantities or symbols in this formula are defined here, right? So capital M sub each refers to the atomic mass of the hydrogen atom. Small letter m sub n pertains to the atomic mass of the neutron particle. Of course, capital C is the atomic number, right, of the element. All right, so the symbol capital M with its atomic number capital Z and mass number capital A, of course, represents the atomic mass of the neutral atom contained in the nucleus, which in our problem is lead-206, or the atomic mass of lead-206. Also, capital N pertains to the number of neutrons. So, computing the mass deficit delta M of lead-206, right, using this formula, we have delta M equals 82, right? That's the atomic number of lead-206. And then we multiply that by the atomic mass of hydrogen atom, 1.007825 atomic mass unit, plus, right, the number of neutrons in lead-206, which is 124, right? Given this symbol, the mass number is 206. 82 is the atomic number. So if we subtract 206 minus 82, we get 124, which represents the number of neutrons. And then multiplying it by the mass of a neutron particle, 1.008665 atomic mass unit. And then we will deduct, all right, the atomic mass of the neutral atom that contains the nucleus, right? Atomic mass of lead, that is, equal to 205.974440 atomic mass unit, right? So when we do our math, we get the mass deficit delta M equal to 1.74167 atomic mass unit, right? Take note that in our computation for delta M, we use the atomic mass of the hydrogen atom, all right? And not the atomic mass of the proton. This is because we wanted to eliminate the atomic masses of the 82 electrons that is included in this atomic mass of the neutral lead-206 atoms. right? So the number or the atomic mass of lead-206, which is 205.974440 atomic mass unit, okay, includes the mass of 82 electrons, right? And then, since there are 82, right, electrons contained in the neutral lead-206 atom, right, uh, multiplying the atomic mass of a hydrogen atom by the number of protons or the number of electrons, and that is 82, all right? In the process of determining delta M, all right, we, in effect, are able to eliminate, right, the total mass of the electrons. In other words, when we subtract the atomic mass of the neutral lead-206 isotope, all right, we also have removed, okay, the total mass of the 82 electrons. So we are sure that the result, okay, of computing the mass defect or delta M, this value 1.74167 atomic mass unit does not include the mass of the 82 electrons, right? So that is the reason why uh, we use the mass of a hydrogen atom instead of the mass of a proton, right? For question letter B, what is the binding energy in million electron volts, right? So, as earlier presented, okay, we use uh, Einstein's equation E equals mc squared, or the energy mass equivalence formula, right? That is, um, the mass deficit that we earlier calculated equal to 1.74167 atomic mass unit will be multiplied to 931.5 million electron volts per atomic mass unit. We call this the conversion factor, right? If the mass is expressed in atomic mass unit, then we just multiply it by this conversion factor. How we got this conversion factor, of course, is still based on E equals mc squared, right? It's quite lengthy, right? If you are going to calculate the binding energy using the units or the SI units, right? Because you need to express the mass deficit in kilogram, right? And then multiply it by the square of the speed of light, which is in the unit meter per second. Then eventually, you will be getting the binding energy in joules, all right? But since what we want is the binding energy expressed in million electron volts, there is a need for us to still convert the binding energy induced into electron volts and eventually into million electron volts. So for simplicity, right, we just use this method of multiplying the mass deficit. Anyway, it is expressed in atomic mass unit, all right? So using the conversion factor, it is a much easier method, right? Like in here, right, when you do our math, we will be getting the value of the binding energy equal to 1,622.4 million electron volts, right? So this is the total binding energy, right, for lead 206, which means that all the 206 protons and neutrons which are intact in the nucleus, right, they are kept intact in the nucleus because of this binding energy, a total of 1,622.4 million electron volts. So, answering question letter C, which is finding the binding energy per nucleon, right? So, we simply divide the total binding energy that we have in letter B, divide it by the number of nucleons. Number of nucleons is equal to 206, all right? When you say nucleons, this is a collective term referring to either proton or neutron. So, simplifying this, we finally get the binding energy of lead 206. Okay, the binding energy per nucleon equal to 7.876 million electron volts. That is per nucleon. So, this value is a relatively high value for binding energy. And this agrees with the fact that lead 206 is a stable isotope of lead, right? The higher the binding energy of an isotope, the more stable the isotope is. So that's it. We are done. Till the next episode, mabuhay, Masya Allah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.